Okay, welcome for part 2 of Matt Novack's lecture series on anomalous dissipation and strong Onsager conjecture. Yeah.
Thanks for coming back. So today we're gonna get into the weeds of these Nash iterations, and I have 3 goals. I don't know if we'll get to all of them, but hopefully at least the first 2. So the first goal is just to set up the Nash iteration. So basic setup. And then once you have the basic setup, I want to understand where these various regularity thresholds come from. And I'm not going to keep you in suspense. I mean, the thresholds that we're going to see are in C alpha, C1/4 looks like the best that you can do. So what's up? And on that note, I should say what's been proven in C alpha. So the first example of this sort of scheme with the local energy inequality was due like that. Again, ignore that. He got C1/15 minus or something like this. So not very close to 1/3, but it was a nice paper. He set up the equations, and we're going to use the equations that set up for us. And this was improved somewhat by Anomalous and Kwan. And they improved to C1/7 minus. So you'll notice that both of these are not up to the C1/4 minus. And that's because there's other difficulties that one encounters in running these schemes. And I'm not going to explain those. I just want to explain one which to me looks like the most fundamental. And that's the one that tells you that even if you solve all the problems that plague these iterations, you still only are going to get C1/4 from what I can tell. So I'm going to explain where this comes from.
And all of these are completely non-intermittent, so they are L infinity based, right? Or
yeah, L infinity based. So this means building a solution in C alpha. This means building a solution in B alpha. That's what I mean by L infinity based. And after discussing these C alpha obstructions, I want to explain why L3 works. So B1/3 minus 3 infinity is optimal for L3. And if we have time, although I'm not sure if we will, and in which case we'll just pick up here tomorrow, I want to set up the L3 iteration. So it'll have, of course, a fair amount in common with the C alpha iteration, but of course there are some differences which we should get to. Okay, so let's set up a basic iteration in C alpha. With the goal of leaving alpha for the moment undetermined. And computing the optimal alpha. Find alpha max. Okay, so this basic iteration is following that. All right, so the plan is to build a solution U of Euler plus local energy inequality. And you will be the limit as u goes to infinity of uq. And this limit should hold in C alpha topology. And you should think about u and q as a frequency projection of u. So I guess I'll write it. I'll write it over here. So think about uq as a frequency projection in space x of the final solution, the limiting solution u, and this number lambda q is going to be a to the b to the q, where b is going to approach 1 from above as alpha goes up to alpha max. Meaning that when you run the iteration, your frequencies grow super exponentially, but as you optimize the scheme, they're barely growing super exponentially and you're almost growing geometrically. Okay, and now what's the equation which will be satisfied by uq? So so the first equation is a relaxation of the Euler equations, or the first part of the Euler equation. And you should think of this divergence of RQ as divergence of UQ tensor UQ minus U tensor U, right? Because if I had a solution of the Euler equations U, and I wrote down the equation, and I modified the equation, I would get exactly this commutator between modification and multiplication. So this is how you should think of the Reynolds stress. And I'll also put divergence of U equals 0, or U equals 0. So this is the first part of the relaxation. I'll often refer to this first equation by Euler-Reynolds, even though Euler-Reynolds technically also includes this. Euler-Reynolds is this first relaxation. And now we need a relaxation for the local energy equality. So that relaxation will look like now I have to put something on the right-hand side. And the something that I'm going to put on the right-hand side will look a little strange for the moment, but in a few minutes, we'll see why I've put this stuff on the right-hand side. And as I run this iteration, I want RQ to converge to 0. It'll converge to 0 in L infinity.
What do you mean by UQ RQ? Like you're taking some product?
Yeah, so this is a symmetric matrix, so you can do it whichever way you like it. So I want RQ to converge to 0 because then I can pass the weak limit over here. I want UQ RQ to converge to 0. So I can pass to the weak limit in here. And that'll also give me convergence in the UQ.nabla trace RQ term. And then I need also phi q to converge to 0. All right.
What do you want the convergence in you cannot do one?
L1 would be sufficient, but in this setting, they're going to converge in L infinity. So I'm just saying that that's what we're going to do. But that's a good one. In the L3 setting, they will not converge. So, okay, so this is our setup at stage Q. And I have to tell you now how to progress from Q to Q plus 1 so that we can eventually take the limit. So we have to add, I'll call this WQ plus 1 equals UQ plus 1 minus UQ. And in keeping with our heuristic about frequency projectors in space, you should think of this as the projection in space of U on the frequencies in between lambda Q and lambda Q. So I'm filling in the frequency shells of my solution step by step.
Now, what's the X mean again in the DX?
It's Littlewood-Paley projector in the spatial variables only. So I'm just projecting onto space frequencies. Okay, and we will construct WQ plus 1 in a smart way, so that these relaxed equations spit out the thing that I expect to find at the next step. All right, so we'll UQ plus 1 equals UQ plus WQ plus 1 into relaxed equations and collect whatever remainders we find. So and collect and estimate remainders. All right, so let's do this first for the Euler-Reynolds bit of this relaxation. So let's do this first equation. All right, so first, plug UQ plus 1 into Euler-Reynolds. And all right. I'm just going to plug UQ plus 1 in on the left-hand side. I'm going to leave the pressure alone for a moment. And on the right-hand side, what will I find? Well, I have all the UQ terms, which from my inductive assumption will give me divergence of RQ. I have the nonlinear interaction of WQ plus 1 inside of this UQ plus 1 with itself. And this first error, we refer to this as the oscillation error. That's the usual phrase. And I guess I'll add the preface Euler-Reynolds oscillation error, because in the moment we'll have another oscillation error coming from here.
Can I ask a question? What is the difference between the WQ plus 1 and the actual Littlewood-Paley projection? Why is it approximate? I mean, how would you describe it?
There's maybe an exponentially decaying tail of frequencies that I'm just ignoring. Those are minuscule, and we'll pretend that they don't exist. That's a fair point. Okay, so this is the oscillation error, and then we have some errors which involve UQ interacting with WQ plus 1, and those are BT plus UQ dot nabla, WQ plus 1, and WQ plus 1 that WQ. And we call these errors on the second line, respectively, transport and Nash. So ER transport plus ER Nash. All right, so the first thing to do is examine the oscillation error because it will tell us how we should construct WQ plus 1. All right. So let's examine the oscillation error. So I just want to do a simple example. So let's assume that this symmetric tensor, I could have said that that's maybe why you asked what I meant by this product. I should have said that this is a symmetric matrix. Which
I was just confused by the position of the vector.
Yeah, yeah.
Rather than multiply by
if it's not symmetric, then maybe it makes a difference. But it'll always be symmetric. All right, so I want to assume that this is just something in the top left component and then zeros everywhere else. We ought to at least be able to treat this case. And I'm going to assume, and you'll see why in a second, that this function that appears in the top left is greater than or equal to 0. All right. So what I'm going to do is set what I want is I want WQ plus 1 to help me get rid of RQ because I don't see RQ in the next version of this equation. I should have RQ plus 1. So I need to get rid of RQ, and that means that these two terms have to cancel in some way. And so what we're going to do is set WQ plus 1 comma R. So I append this with an R because I'm just going to split WQ plus 1 into something which helps me deal with the phi's and something which helps me deal with R's. And I'm just dealing with the R's for now. So we're going to set this to be cosine lambda q plus 1y r cube r times 2 and 1/2. All right. So you should think of this as low frequency coming from here. And by low, I mean at lambda q. And what I've multiplied this low frequency thing by is something which is high frequency. High frequency shear flow. So a shear flow this is an example of a shear flow. The oscillations are only in the y variable and the velocity is in the x variable. So and the point of having oscillations in the y variable and velocity in the x variable is that this is a stationary solution of the liquid. So you can check that shears are stationary solutions. All right, so with this ansatz for WQ plus 1 comma R, let's see what happens in this nonlinear error term. All right, so it was the divergence of RQ, and let's just keep track of the WQ plus 1R. Obviously, there's some coupling between these two things, but just ignore that for the moment. Let's just deal with this guy. Okay, so if I write this out, I only have non-zero components in the top left, coming from this guy tensor with itself and RQ. So this is some vector which points in the E1 direction times divergence of E1 times what did I do here? Yes, minus coming from up there. And then coming from here, I have 2 RQ bar cosine squared lambda q plus 1. And now let's factor out the RQ bar from both terms. Minus 1 plus 2 cosine squared lambda q plus 1y. And I set this up so that we have a trig identity now, which tells us that minus 1 plus 2 cosine squared is equal to cosine of twice the name. So cosine of 2. All right. Another way of thinking about this is what we've done is we've said that WQ plus 1 comma R tensor WQ plus 1 comma R. This is something high frequency tensored with itself that's going to produce low frequencies plus high frequencies. So if I split this into low and high, I'm using the low frequency part to help me get rid of the low frequency RQ. And all that's left over then is just the high frequency part, which is this part. Okay. And now we let the divergence land on the vector field inside. So it's E1 times something, which means I'm only seeing derivative in the x direction. And so I'll have dx of the RQ bar, and then cosine of lambda q plus 1. And what we've used here is we've used basically the stationarity of shear flows to say that the differential operator didn't land on the high frequency object, right? It's a stationary solution of the PDE. So when the derivative lands, I get 0. All right. So this is now our computation of what's left over in the oscillation error, and now we want to estimate this. So what's this? And in order to estimate this, I need to tell you how big I expect this to be. All right, so let's make some size considerations. We said that WQ plus 1R was like, morally speaking, RQ to 1/2 times cosine of lambda Q plus 1y. And this was high frequency times low frequency. And so this object lives basically at frequency lambda Q plus 1. It's the projection on the frequency lambda Q plus 1 of my final limiting solution U. And if I want U to be in C alpha, then the projection on the frequencies of size lambda Q plus 1 ought to have L infinity norm lambda Q plus 1 to the minus alpha. Actually, let me switch this to a beta. Because otherwise I will surely confuse myself with the names of these parameters.
How wide is this shell? I mean, what do you mean it's?
Think of the frequencies as just not a continuous, not just as a discretized sequence of lambda Q plus 1, lambda Q plus 2, and I'm adding the bit that lives in lambda.
Yeah, I see.
All right. So if this is size lambda Q plus 1 to the minus beta, then RQ ought to be of size lambda Q plus 1 to the minus 2 beta. Because I have RQ to the 1/2. And I'm going to call this parameter delta Q plus 1. So let's see, let's maybe let's write delta over here, and I'll try not to erase this board so that we can keep track of the locations and whatnot. All right, now notice that the errors on the right-hand side of this equation, this Reynolds equation, are always in divergence form. And what we have left over here is not in divergence form. So I have to integrate it to put it in divergence form. So I'm going to define the oscillation error component of the next Reynolds stress to be basically the inverse divergence of this vector field. So and I put squiggly here because this isn't the scalar inverse divergence, it's eating a vector and spitting out a symmetric matrix, but that's an algebraic consideration that I don't want to think about. So just think about this as a -1 order Fourier multiplier, which gains the minimum frequency of the input. So think about this as basically a -1 order Fourier multiplier. All right. Now, gains minimum frequency of input.
Minimum will be enough, right? Because minimum is frequency of the previous RQ.
No, the minimum frequency is lambda Q plus 1. When I multiply two things together at frequency lambda Q plus 1 and lambda Q, I get something which is a frequency lambda Q plus 1 minus lambda Q, which is still size lambda Q plus 1. So here's an example. integrate in one dimension sine of lambda q x sine of lambda q sine of lambda q plus 1x. And you'll see that this is O of 1 of them. Integration is like inverse divergence to me. Okay. All right. Let's go back over here and now work on the size of this thing. Okay, so how big should this be? So the size of divergence inverse of this RQ plus 1 os. So let's just put dx RQ bar cosine lambda q plus 1y. The divergence inverse, that's like integrating. It'll gain lambda q plus 1 in the denominator. The dx, well, RQ, we said was size delta q plus 1. And I know that RQ has only frequencies less than or equal to lambda q because it's written as this commutator between multiplication, multiplication, and frequencies lambda q. So dx of RQ is going to cost the infinity norm of RQ times the maximum frequency, which is lambda q. And if I want to close my inductive iteration, if this was delta q plus 1, then this ought to be delta q plus 2. This is what I need in order to close the induction. All right, so what I need is delta q plus 1 lambda q over lambda q plus 1 less than or equal to delta q plus 2.
Sorry, I have a question. So I mean here you are using that like probably everything is like smooth because I mean otherwise like your Fourier multiplier will not give infinity.
Yeah, yes.
So I mean you are like saying yeah okay everything is smooth so I can get to infinity.
Yeah, assume that I have very high derivative estimates, basically coming from frequency projectors on everything which appears in these equations.
Okay.
All right.
Yeah.
All right. So this inequality, we need to do a little bit of arithmetic. So by the definition of lambda q and lambda q plus 1, I have the lambda q plus 1 is lambda q to the b. If I raise this number to the b, then I have b to the q plus 1, and that's lambda q plus 1. All right. So I'm going to write everything in terms of lambda q. So this delta q plus 1 is lambda q to the minus 2 beta times b. The lambda q up here gives me a 1, and lambda q plus 1 in the denominator gives me a b. And on the right-hand side, I have delta q plus 2. So that's lambda q to the minus 2 beta b squared. And this inequality will hold if and only if 2 beta b squared minus 2 beta b is less than or equal to b minus 1. So I move this over onto the left-hand side, and I move the b minus 1 over on the right, and then I compare by taking the logarithm. And this tells me after factoring b minus 1 out of the left-hand side, that beta is less than or equal to 1 over 2b. All right. So as b goes to 1 from above, the best regularity that I can get is C beta, which would be C1 half. So this tells me that at least in this setting, this nonlinear oscillation error is not sharp. Yeah, ER oscillation is not sharp.
I mean, not the worst one.
It's far above the C1/3 threshold that I would. I'm going much slower than I anticipated, but is it too slow or is it okay? Okay, we'll keep it this pace then, and we'll get through what we get through. All right. So the point is, and this is kind of weird, I have a nonlinear PDE, and I looked at the error term, which was quadratic in the high frequency object. You think that would be the worst, and it didn't seem so bad. I got that this error term is at least consistent with C1 half minus regularity. Strangely, in order to find the 1/3 threshold, in this setting, I look at the linear error terms. So let's look at one of the linear error terms. So we did Euler-Reynolds oscillation. Let's do Euler-Reynolds Nash. And the Nash error, I guess I probably erased it. It was WQ plus 1 dot nabla VQ, which I want to write in divergence form, right? I want to write this as the divergence of some Nash error, which means that morally speaking, what I have to do is apply my inverse divergence to this. WQ plus 1 by nabla. All right, let's see how big this is. So we have divergence inverse. Now, WQ plus 1 was, morally speaking, it was like RQ to the 1/2 times something which was high frequency. I'm ignoring this, this is a vector field. Just think of it as a scalar, and its size was given by this product. And I also have nabla UQ here. All right, so just like before, this will gain lambda Q plus 1 inverse. This will cost delta Q plus 1 to the 1/2. It's the square root of the Reynolds stress RQ. Size of this is 1, so it's not doing anything. And nabla UQ, what is this? This is nabla of WQ plus nabla of WQ minus 1, all the way on back down to my first W0. And the size of the most recent WQ is going to be, well, it'll be not delta Q plus 1 to the 1/2, the delta Q to the 1/2. And because it's at stage Q, where everything has been projected on the frequencies less than or equal to lambda Q, the nabla is going to cost a lambda Q. And if I go back to the previous term, then I'll get delta Q minus 1 to the 1/2 lambda Q minus 1. And the point is that this is the series, for which the most recent term is the biggest. So that's the only one that I'm going to look at in terms of size. And so the size of this is delta Q plus 1 to the 1/2, delta Q to the 1/2, lambda Q over lambda Q to the 1. And I would like this to be less than or equal to delta Q to split. All right. Now let's do the same thing where we write everything out in terms of lambda Q and compare the exponents. So this is going to be lambda Q to the minus beta B from here, lambda Q to the minus beta from here, lambda Q to the 1, lambda Q to the minus B, lambda Q to the minus 2 beta B squared. And now we compare, and we have 2 beta B squared minus beta B minus beta ought to be less than B minus 1. All right, so let's factor beta out of the left-hand side. So I have 2b squared minus b minus 1. That's a polynomial that I can factor, and I get beta 2b plus 1 times b minus 1. That's going to give me 2b squared plus b minus 2b gives me minus b. Sorry, minus 2b plus b gives me minus b plus 1 minus b gives me minus. All right. So as b approaches 1 from above, we're going to get C1/3 out of this. All right. So the Nash error is the error term, which if I ignore the local energy inequality and I just try and build a solution of Euler, it's going to limit my construction to C1/3 minus regularity. All right. Let me pause to erase and then also pause, see if you guys have questions. So that was the Euler-Reynolds part, and we found the 1/3 threshold. Now, what we have to do is plug WQ plus 1 into the equation, which I'll call the relaxed local energy inequality. So it's the relaxation of the local energy inequality. So let's call this R. Now, there's a lot of terms in this equation, and so let's say I'm going to censor this calculation, but you could just plug in WQ plus 1 and see what's left. And the reason I'm censoring this calculation for the moment is because it's tedious, and I just wanted to highlight the analog of the Nash error. So we find an RLEI type Nash error, which if you had written out all these steps, what that term looks like is this. You can think of this, morally speaking, as the dot product of WQ plus 1 dot anomaly UQ, but projected onto high frequencies. So projection on the lambda Q plus 1 of this dot product. Right, because the way I derive the local energy inequality is by taking the dot product of the equation with the velocity field. So the way I find the Nash error in the relaxed local energy inequality is, morally speaking, by taking the dot product of the Euler-Reynolds Nash error with WP plus 1. And because of the way that I've set up the right-hand side, I get that this thing is actually high frequency. That's part of what's contained in this calculation that I'm going to cite in a moment. All right. All right, so I just want to put this in divergence form and estimate.
I wanted to just say a sentence, why is it restricted to below frequency lambda Q plus 1? I mean,
It's basically the projection on the frequencies exactly equal to lambda Q plus 1, and that's because divergence. Good point. Divergence of UQRQ, which I had over here. This contains a term which is novel UQ tensor RQ, and RQ at low frequencies. RQ is the low frequency projection of WQ plus 1 tensor WQ plus 1. So I use this term over here to kill the low frequency part of WQ plus 1 tensor WQ plus 1, and I just get the high frequency part as the left. That was a good point. I should have just said that. All right. So let's estimate this, and maybe let's go on to the board edge. Let's leave this total. About to see the 1/4. All right, we do our usual thing. The divergence inverse means lambda Q plus 1 inverse. WQ plus 1 tensor WQ plus 1. That's exactly the same size as RQ. And the size of RQ was this delta. So this is delta Q plus 1. It's just another extra delta Q plus 1 to the 1/2 compared to the estimate that I had. And this is delta Q to the 1. And the question is, how big should this be? And I claim that what I want to find is hopefully delta Q plus 2 to the 3/2. And why do I say hopefully delta Q plus 2 to the 3 halves? Well, it's because if the size of WQ plus 1 squared was delta Q plus 1, that's what we used in order to enact the cancellation over here between RQ and WQ plus 1 times WQ plus 1, then WQ plus 1 times the modulus of WQ plus 1 squared. This is something which will appear in my trilinear oscillation error. Then I have a hope of cancellation between equals 0 at low frequencies if the size of this phi q is delta q plus 1. All right, so what am I saying here? I'm saying that we used a quadratic interaction to kill RQ, WQ plus 1 times to WQ plus 1. That told us how big RQ ought to be. We're going to use a cubic interaction between WQ plus 1 and itself to help us get rid of this phi q, which means that the phi q ought to be of size delta q plus 1 3 times. All right, and if this is size delta q plus 1 to the 3 halves, then I'm hoping that this next error term is the next delta to the 3 halves. That's what I need in order to close the iteration. All right, so let's write out.
Can you see it directly from UQRQ in the way that we've written it? I mean, it's delta Q to power 3 over 2, right?
So there is an error term coming from there which has the same size. You're right. I want to highlight the Nash error because it draws a nice analogy with the Euler-Reynolds Nash error. And it's called Nash because you see the same error term in the scheme for the isometric embedding, and that's what's inspiring the Nash iteration to begin with. So in some sense, it's one of the most fundamental error terms. And if we can't get that one to work, then we're probably toast. And that's why I'm writing out this Nash term. All right, so what's the size? It's lambda q plus 1 inverse in the bottom, a full delta q plus 1, and a delta q to the 1/2 lambda q. And I want this to be less than delta q plus 2 to the 3 halves. So it's the same inequality that I had down here, except instead of delta q plus 1 to the 1/2, I have a full delta q plus 1. That means I'm going to have lambda q minus 2 beta b squared minus beta plus 1 minus b. And on the right-hand side, instead of lambda q to the minus 2 beta b squared, I have lambda q minus 3 beta b squared. All right, so I factor this like I did before. I move the 3 beta b squared over to the left. 3b squared minus 2b. Sorry, this is not beta b squared. This is beta b. Yes, beta b. Coming from minus 1 less than or equal to b minus 1. And I factor this polynomial just like I did before. And now this factors as beta. 3b plus 1, b minus 1, less or equal to b minus 5. And this, very sadly, tells me that beta, best case scenario, is 1 over 3b plus 5. All right. This is where the 1/4 comes from. And this is why we worked in L3. I really have I have no idea how to circumvent this issue. It's a bit frightening because even before I proved the Onsager conjecture, people had kind of eyeballed the Nash error, and they had seen the 1/3 popping out, and they told themselves, hopefully this will work someday. And you do the exact same thing with a relaxed local energy inequality, and it doesn't work. All right, so I think I'll actually stop here because I don't want to try to explain in 4 minutes why working in L3 fixes this issue. So let's just say pick up tomorrow with why L3 ranks the 1/4. All right, so I'll stop there and thank you.